All right, we're good. Yes. You need a syllabus as well? All right, again, welcome. This is Math 209. Elements of calculus and statistics, basically the calculus 2 for bio majors, some psychology majors, economics majors can also take this, I guess. And last time we went over the syllabus and some of the important things we need to remember from Math 205, such as derivatives and integrals of various kinds of functions, including ones with exponentials and logarithms. And last time I actually wrote down all the rules. We talked about the power rule, the product rule, quotient rule, chain rule, all of that. We did it with e's and ln's. We also talked about the integral rules. We talked about substitution. Here I have some extra examples just to hit it home, make sure that we understand what's going on. And then we'll move on to chapter 2. So chapter 1 was basically just a review. And we sort of did mostly a review last time. So let's just go through some examples and then move on to chapter 2. These are examples for integrals, because we're going to be integrating all the time in this class. It's the first one. How about the first one? What did you do? Apply the sum rule? Sure. Which basically says we can distribute an integral across the sum, so we can just look at these as 3 separate integrals. Okay. How do I integrate the first? At the exponents, what's the exponent of this guy? Right, radical x you think of as x to the half, right? So this is just like 3x times x to the 1/2. You add the exponents to simplify it. So we can actually rewrite this as 3x to the what?
3 over 2.
3 over 2. Plus x cubed minus 2 dx. And now what? How?
Add 1 and divide by the exponent.
Okay, so when I add 1 to 3 over 2, what do I get?
5 over 2.
5 over 2, you divide by 5 over 2, same as multiplying by 2/5. And that 3 is here. And this one?
X to the 4th over 5 divided by 4 minus 2x plus.
Right, you can't really cancel anything here, so I'll just simplify this by multiplying across. So this is 6 over 5, x to the 5 over 2, plus x to the 4th over 4, minus 2x plus c. And that is your answer. What about this example?
4 inverse
What do you get?
X squared plus 3x equals 2.
Now what? You divide each term by x, right? Take this x, you divide into each term. So we will end up with x plus 3 plus 2 over x dx. And of course, you can apply the sum rule, so we just integrate each term. Integral of x is integral of 3, integral of 2 over x,
2 over x.
absolute value x plus c. Right. What about this one? Substitution, what would you substitute? So I can let u equals ln x, and then what would we do?
Take the derivative of that times 1 over x dx.
1 over x dx, which we have right here.
dx is equal to x.
So this becomes what?
Du times x. Dx equals to du times x. Just multiply. Yeah.
We could do that, sure. We could also just swap this out for du, it would be the same thing. I guess some people like this method when we do that. So now you can start to plug things in. So what would we have?
5 over x u times x du.
X is cancelled. And so you just basically have the integral of 5 over u du, and this is
5 ln x to the value u.
which
5 ln
u was ln. Okay, good. This one? What would you substitute?
x4 minus 7.
Du would be?
4x.
And what can we do here?
So we cross out x. 1 over 4x. Well, I do that on that.
So you like to solve for dx, and you can swap it in here. Okay, so what do we get?
Got 3x cubed over u times 1 over 4x cubed du. And cross out the x cubed.
It's cubes would cancel. This 3 over 4, there's a constant factor rule. We can always factor constants out if we'd like.
It's just 3/4 ln absolute value u plus
U was x to the 4th, and 7 plus c. I think I made a typo with this one, but how do you try this?
substitute 4x cubed minus 3x.
Right, substitute the power of the exponential, because that's what's making it complicated, and so
That
we
should
would
be
have
4x squared minus 3.
u is equal to 4x cubed minus 3x. Your du would be
12x minus 3.
dx. Does that help?
Yeah, you can get rid of the x. You can take out 3, right?
3 is a common term. I can factor out a 3, and I'd be left with
4x cubed squared out of minus 1. And now you can
and then you can do your little division maneuver if you like it that way.
How would you, what's the other way of doing it?
Well, this is sort of like just plug it in directly from here. You didn't have to do the extra stuff, but it's completely fine. So now our integral becomes we have this 4x squared minus 1. E, we replace the power with u. And then the dx, we replace that with this du over 3 times 4x squared minus 1. This cancels. This is a third, right, because it's in the denominator, so I can actually factor that out. And what's the integral of e to the u? This is just 1/3 e to the u plus c. Okay. Is it all coming back? Good. We're going to need it. And we're going to need it pretty much now. We're moving on to chapter 2. So chapter 1 was all about the review. We did most of the review last time. So just to make sure that we have we're moving on to chapter 2 where we talk about differential equations. Or the ones we will be looking at, ordinary differential equations. Which we might call ODEs. So we're just going to start to talk about what they are and how to solve them, and then we'll actually do applications later on, because these do apply to some things we'll be looking at. They apply to populations, ecosystems, money in a bank account, all sorts of stuff. Right? So, but now we're going to treat them very abstractly as just this mathematical thing that we're going to do, and we're going to be applying it later on. So just to get this on the road. So an ODE is an equation that involves the derivatives of a single variable function. Right? So basically equations with derivatives in the equation itself, we call those differential equations. When we just have regular derivatives, we call it ordinary differential equations. We also have partial differential equations, but it's not in our scope, so we won't worry about those. But basically any equation that has a derivative in it, we call it a differential equation. So for example, if I give you that equation, that's a differential equation because there's a derivative of a function in it. Or I can say y prime equals y, that's also a differential equation because it has a derivative in the equation itself. So that's what they are. Basically, to solve a differential equation, we want to relate x and y, if possible. Write the solution in the explicit form. Right, so y equals f of x. Right? So basically, I'll be given an equation like this, and I basically want to find y, find that function that makes this equation true, right? So here I'm telling you there, for example, there is some function where if you take its derivative, you get the original function back. What kind of function would obey this rule, right? It's basically what we're doing, Right? Can anyone know what kind of function it is that would be? No, I need the function y. Can you tell me a function that when you differentiate it, you get itself? E to the x is one such function. In fact, a constant times e to the x is such function. All functions that look like c e to the x would be a solution here, right? So for this example, for y prime equals y, y equals c e to the x is the general solution, right? Basically, I just found y equals f of x, right? I wrote y as some function that if that's true, this will necessarily be satisfied, right? I just want to find some function that satisfies this equation, right, when I take derivatives into account, right? So that's what we call solving the differential equation. Notice that this c could be anything, right? Any real number can work here. And so that's why this is called a general solution, because it gives us a whole bunch of possible things that can work. If we are given a constraint, it's often called an initial condition. We can find the so-called particular solution. Right? This is the specific function that solves the ODE and at the same time satisfies the initial condition. Example, let's say I have y prime equals y, and I gave you the condition, I would like to find the y such that y of 0 is equal to 1. Right? This here is called the initial condition. Right? This guy here is your ODE. I gave you an ODE, and I don't just want you to tell me a general solution. I want to find a very specific one, the one such that when I plug in x equals 0, the result is 1. Right? So that's a condition I'm giving you to fulfill. So we know here that y is equal to c e to the x. So we can just solve for the c. Since y of 0 equals 1, remember the guy in here would be your x value. Right? The guy out here would be the output y value. This means that my y is 1 whenever I plug in x equals 0. So what would c be in this case?
1.
Right, e to the 0 is just 1. So right, so we get c equals 1. And so y equal to 1 e to the x would be the solution I'm after in this case. Right? I could give you some other condition and you'd have obviously a different value for c that will satisfy that. Do you understand what's happening so far? So a lot of things in real life are modeled by differential equations, which is basically equations that have derivatives in them. Sometimes we don't care about the derivatives, we want to get back to the actual function that's being considered. And there are two kinds of solutions we can find. We can find a general solution, which is just a family of functions that will work. And if we're given a particular constraint, we can find the particular solution that fits that constraint. Right? If possible, not all differential equations can be solved, but we're going to be looking at some that can be solved. And right, so this is sort of the idea behind them. Now, the thing is, with this equation here, it was sort of easy for us to just see the answer, right? The derivative is itself, right? We know a function like e to the x, that was easy. It's not always that easy, so I'm going to tell you about some techniques. Well, we're really only going to do one real technique in this course for differential equations. Well, we're going to do a couple. But one where you actually work out the answer algebraically, we're going to be doing basically one technique. And like I said, we'll use this later on, so you'll see how it all ties into what we're going to be doing. But we're going to just get through the math behind it for now. Let's see. Again, if applicable, it's not always the case that we can do this. Sort of just one of those things you have to look for. It's called separation of variables. As the name suggests, we separate the variables, right? We try to get all the x's on one side and all the y's on the other side. You get all y's on one side, all x's on the other side, and then integrate to get to y, right? This is one of the reasons why you're going to need to remember how to integrate things. Like I said, a lot of real-world problems are going to be modeled by differential equations, and a lot of times in order to solve them, we're going to have to integrate things. So let's go over this same example. It's an easy one to do separation of variables, but I'd like you to just see it on an easy example first. So let's say for a second you forgot about e to the x is the guy that if you differentiate you get it himself. Right? I mean, I know that'll never happen, but let's pretend it did for a split second. Right? So you have y prime equals y. How do you get to a solution if you didn't just see it? Well, try to write it in this form. Right? So if y prime equals y, if I'm assuming that my independent variable is x, I can write y prime just means dy dx. How can I separate the variables to write it to look something like this? Cross multiply. So I basically get dy equals y dx. Divide by y on both sides, sure. So 1 over y dy is equal to dx, right? And that is of this form, right? This is just 1 over y, your g of x is just the function 1, right? And now what we can do is we can actually integrate both sides. What's the integral of 1 over y? What's the integral of 1?
X.
X plus c, right? So technically there's a plus c on both sides, but we always bring it over to the right side and just concentrate into one big C. All right, so now if I wanted to get to the y, what would I do? I want to solve this equation for y.
Take the exponent.
Take e to both sides, right? Because remember, logs and exponentials are inverse functions, so if I want to get rid of an ln, I need to put an e in there so that they would cancel. And so this would give me y is equal to e to the x plus c, which I can basically write as c e to the x if I wanted to, right? Why can I write it like that?
Oh, because it's e to the x plus e to the c.
Well, times, right? If you have e to the x plus c, that's just e to the x times e to the c, and then that's just a constant. I just call it a big C, right? Technically, these two c's aren't the same, but who's keeping score? Now, remember, absolute value y means sometimes you can put a negative there or a positive there, but since this c is arbitrary and we can sort of solve for the one we need, we don't need the absolute values here, so we can literally just drop it. And we get back to our solution. C e to the x was the guy we were looking for all along, right? So there are cases where we can't just see the answer, but we have one technique at our disposal. This is the first non-trivial technique, and we're not going to be doing many more algebraic ones. But this is a really nice one that we will be able to use a lot of the time in this course. Separation of variables. You have an ODE you want to solve, try to get all the y's on one side, all the x's on the other side, and integrate both sides. And then do whatever algebra you need to do in order to solve for the y, right? And so doing that, we can get to the general solution, and if we're given a condition, we can find the particular solution. Any questions on this? Any questions? Okay. Now let's do another test. ODEs where this technique would be where? ODEs for which this technique works are called separable ODEs. So if I say this differential equation is separable, it means this sort of technique can work. It can't always work. I want to emphasize that. There are things that we can't separate the x's and y's and get something of this form. So let me see if you can recognize them. Tell me if these are separable or not. One more, but there's no space for it. All right, separable or not separable? Yes.
So in order for it to be separable, you need to get that. So then there's the y.
No, separable means you can write it in that form. It means you can write it as f of y times dy equals some other function times dx, where you only have x's as the variable here and only y's as the variable there. That's what separable means. You can actually separate them. Can you do that? Can you write this to look to be in that form? Is the question.
Yes.
Yes. All right. How would you do it? There's a common y, right? You just factor it out. You only have x's left, and you divide both sides by the y, right? And you get the y on that side, bring this dx over, and you're done. What about this one? Separable?
You could subtract.
No. It's not separable. Why not?
Why couldn't you bring like negative 5y up, or 5y to the other side?
Let's try to separate it. What if I did it as you suggested and subtract 5y from both sides? Now
Hold
what?
on,
The x isn't the common cap.
Yeah, that's what point, right?
Right. It's not a multiplication times dy. I'm subtracting it. And my problems actually don't end there. See, now I have the task of bringing the dx to the other side,
Right.
but I can't do that without affecting this guy. Multiplying both sides by dx to move him over is going to multiply this y by dx. And so once I try to get rid of the x's on that side, I'm going to have this y stuck with an x. On top of that, there's a plus or minus sign in between here, right? Notice that what you need, multiplication and division. Meaning if something is separable, you have to be able to get it in this form using only multiplication and division to move things over the equal sign, right? So if you have to subtract, it's not separable. It just won't work, right? You won't be able to separate. So that's one of the things that you need to notice about this form. So that's actually not separable, right? So I couldn't use the trick I just used on this particular differential equation. I would need some other technique. What about this one? Separable? Yes, no? Yes, it is separable. Right? The kind of function doesn't matter. All that matters is I can separate x and y's and look like that, which I could here, right? If I had dy dx equals y squared minus 1, what I could do is I could multiply both sides by dx. And then just move this whole function underneath, right? I can write this as dy over y squared minus 1 equals dx. Right? And that is the separable case. Of course, integrating this, you can't really do unless you've done math 202, but that's beside the point for this exercise. Separable or not separable? Separable. Multiply both sides by this, multiply it by dx, and you'd actually separate x's and y's. And that one you could integrate and actually solve for. This one you need a different math class. You need a different technique to actually get to the answer. What about e? Separable or not separable? Right. There's no way you can get rid of this y without affecting that 2. Right? So once you try to divide by y on both sides, that's going to be divided. Right? And so it's not separable. This one.
Because y is not.
Not separable? Separable? It is separable. Okay, so you said it was. What did you see?
Well, you could take out the x,
Take out the x.
x squared, take out an x squared.
How?
Can't you move x squared plus 1 over to the other side and then divide?
How would you move it to the other side?
I'll add x squared plus 1.
Remember, we don't want to add to get to the other side. It messes up the form. If you're moving things to the other side, you should be multiplying or dividing, or it won't work. So she's thinking factor by grouping. So this is y times x squared minus 1. I can factor out a minus sign here and get x squared minus 1. What does that mean? So this is just y minus 1 times x squared minus 1. And clearly it's separable from there, right? Just divide by this guy and then move the dx over. Right? So this is actually separable. Okay. Now, assuming these are separable, solve the differential equations. Which, by the way, I know it's day 2, but this is actually pretty fundamental. You're pretty much guaranteed to get a problem like this on your final. It's pretty much guaranteed to be problem 1 on your final. Where they're going to tell you, part A, solve this by separation of variables, and they're going to probably ask you to do some other techniques with it afterwards. Right? So this is important stuff. Right? You will be tested on this. Right? So they're going to give you a differential equation that says solve it. They probably won't say separation of variables, but it's going to be the best way to go. All right, so start with A. How do we solve that? I can multiply this dx over, sure, to get that dx, and then what?
Y to e to the negative y.
E to the minus y, I also divide, right? So what does the left side become?
dy over e to the negative y.
Okay. This becomes 2x minus 4 dx. That's clearly separable. And how would I integrate this? How would I deal with that 1 over e to the minus y?
It's 1 over e to the negative y, so it's e to the 1.
It's e to the y, right? You just flip it and make the power positive. So this is just e to the y dy equals 2x minus 4 dx. Integrate both sides. Integral of e to the y. It's just e to the y. Integral of 2x. Integral of 2x.
Minus
X squared minus 4x plus c. And how do I get to the y? I want to solve for y. I log both sides to get rid of the e. And so you would end up with y is just ln of x squared minus 4x plus c. That is the general solution to this equation. So if y is this function, then its derivative will be equal to this expression. Yes?
Can you explain what you did with dy over e to the negative y?
Well, there's a law of algebra that says this is true. Right? I just flipped it. Right? So if I have 1 over e to the minus y, that's just 1 over e to the y. Multiply fractions and flip and multiply. So you cannot, things in the denominator, you can move them up and change the power, the sign of the power, and that'll work because of this rule. This one. Don't jump at me at once.
Would you start by, to make the, like I would multiply by dx, but then when you take the integral, there'd be nothing on that side, like dx.
Well, if you multiply by dx, you get 5y plus 2 dx.
Yeah, I'm sorry, I jumped. And then I would divide the y, so like the factor in the parentheses, but then when you take the integral, I'm not familiar with what would happen. So if it became dy divided by that equals dx, and then when you take the integral of that,
Yeah, what is that?
Yeah.
Huh?
1/5 of that.
1/5 ln y.
y.
Right? By substitution. 5y plus 2 equals x plus c.
Oh, so that would just become x if there's nothing there. It would just be
It's
1
a 1.
times. Okay.
You think of it as a
Got
1.
it.
And now I want to solve for y, so what I can do is I can multiply both sides by 5. So this means ln of 5y plus 2 is equal to 5x plus c. C is an arbitrary constant, so whatever arithmetic I do to it, I just keep writing as plus c. It won't matter at the end. And to get to the y, what do I need to do? There's both sides to the e, and so here I have 5y plus 2 is equal to my previous argument c e to the 5x, right? Because this plus c power, I can factor it off. And so in the end, my y is going to be equal to c e to the 5x minus 2 all over 5. That would be the general solution to that. Right, so subtract 2 from both sides and then divide by 5. What about this guy?
Divide e to the x squared minus ln y is 1.
Yes, I can do that. By the laws of exponents. Right? So the subtractive power means it was actually being divided. By the way, what is that e to the ln y squared?
Just y squared.
That's just y squared, because these elements cancel. So this is just e to the x squared over y squared. And now what?
Times y squared.
Multiply by y squared and then multiply by dx, and you would get y squared dy is equal to x e to the x squared dx. You can integrate both sides. This side becomes y cubed over 3. How do I integrate x e to the x squared?
Substitution.
Substitution. Substitute what?
It's going to be 2x.
Alright, so we're going to do u is equal to x squared, the du will be 2x, blah, blah, blah. We're actually going to get 1/2 times integral of e to the u du. And so that's just 1/2 e to the x squared plus e. And so I can multiply 3 on both sides and then take the cube root. So y is actually going to be the cube root of 3 over 2 e to the x squared plus c. And that's the general solution for this guy. Alright, so I skipped some steps here to do the substitution, but I'm hoping you can fill in the gaps. Right, y is a common term in the top, which means I can factor it out. And now what?
How do we get rid of the x plus 2? Well, by because it's some. It's x plus 2 times x minus.
Alright, so notice that there's a difference of 2 squares in the top. Plus 2, x minus 2, x plus 2, these can sort of cancel. And so this would just be 1 over y dy equals x minus 2 dx. And we integrate both sides. So this is ln of y. So now I root both sides to the e, and so my y is equal to c e to the x squared over 2 minus 2x. And that is our general solution. Any questions on this so far? Or so we're getting how these things work? All right, one last example here, and then move on. Okay. How do we solve these?
You divide by y and then divide by x squared plus
All right, I can move this y over here by division, so I get that 1 over y, and I can divide by this. So I get x over x squared plus 1 dx. And the x's and y's are separated, and the dy's and dx's are attached to the function by multiplication. So that is some good separation of variables. So now we integrate both sides, 1 over y, ln y. How do you integrate that?
1 over
So we could solve for y, but I'll probably want to find this c first. Let's say I wanted to find the c right now. How would I do it?
plug in one where there's a y.
Since y of 1 is equal to minus 4, what does this mean? What would the y values be?
Y is negative.
Y is negative
X
4.
is 1.
Now don't worry that it's negative 4 here because it's absolute values, so it doesn't matter. That's just ln 4. And this guy is just 1/2 ln 2 plus c. So I can start to solve for c. So c is equal to ln 4 minus 1/2 ln 2. And remember that ln 4 can actually be written as 2 ln 2. Did I lose anyone? Yeah?
How do you get that one to 1 plus 1?
X is 1. So I just plug in 1 squared plus 1 is 2. Right? ln 4 I can actually write as 2 ln 2, just to write them common, right? Because 4 I can write as 2 squares, and remember a property of logarithm is that you can bring the powers down in the front, right? So I have 2 ln 2 minus 1/2 ln 2, so I just get 1.5 ln 2, so this is just 3 over 2 ln 2. So ln y is equal to plus 3 over 2. Right, so do you see a way to solve for y? You just do each of both sides, right? So this is just y, but what would that side be?
Or you can do ln. It's going to be x. Yeah. X squared plus 1 plus 2 to the 3 second.
Remember that you have this half here.
Yeah, but you can bring up to x squared plus 1, right? You can do it's just radical x squared plus 1.
Right, so you can have x squared plus 1, you bring that half power up here, and then you have ln 2, you bring that 3 over 2 power up there.
Isn't ln 2, isn't that a constant?
ln 2
so
is a
would that go
constant.
in front of the e?
No, not necessarily. We can simplify more, we're in the process of simplifying. What can I do here? There are a couple ways you can proceed.
separate them, right? E,
Separate how?
e to the ln x squared plus 1 times e to the ln 2.
Right, so times, because there's a plus here, it means you have to multiply. So it's just e to the ln x squared plus 1 to the 1/2 times e to the ln of 2 to the 3/2.
And then e and ln's plus
E's and
that.
ln's will cancel out, so what you have is you have 2 to the 3/2 times the radical of x squared plus 1. And that would be your solution in this case. Now, I'm just going to come out and tell you one of the reasons why we use differential equations, and we'll actually later on come back to it and prove it and then use the same sort of equation to do something else. But just an FYI at this time, I'm just going to come out and tell you, under the situation where we're compounding continuously, this actually models the growth rate in a bank account, right? So here, R is equal to, in this case, it would be the interest rate as a decimal. Later on, we're going to come back to this and we're going to realize that a lot of populations are actually modeled this way, in which case R would be the growth rate of the population. Right, but we'll get back to that. But you can use it in finance, and R would be the interest rate. H would be the external change that's made on a regular constant basis. So it's the amount deposited or withdrawn. Per unit time. Right? And T is representative of time in whatever units are appropriate. P would be the current balance. You think of it as a function of T, and it's the current balance at time T. So if you have a bank account being compounded continuously, and you're making a deposit or a withdrawal, or nothing, you could have H equals 0, that's perfectly possible. Then this differential equation will actually model how the bank account will grow. So let's do an example. Like I said, we'll come back to it, but I just wanted you to see this example now. And I think examples that could show up in the homework as well. Okay, so this is the question. You deposit $1,000 in an account, it's growing with compound interest, compounding continuously, growing at 5% interest per year. Right? Per annum means per year. Right? And I want you to write down a differential equation that will describe the situation, solve the differential equation, and then tell me how long will it take to double your money and how much money will you have after 6 years.
It's going to be 0.05
Okay.
times 1,000.
So what is it, the differential equation? dp dt is equal to
0.05
0.05
times 1,000.
p. Right? Plus
1,000.
Remember, the important part of this is per unit time. It's a repeated behavior, right? That 1,000 is not really something that you deposit all the time. That's how much you start with. You put that in one time and you just watch that grow, right? It's not counted as the age. The age is 0 in this case, right? You put $1,000 in the bank and you just watch it. You're not doing anything, right? All right. What's the initial condition here? So I asked for the ODE and the initial condition to describe this bank account. Can you write down an equation that it has to satisfy? Like the amount at some time.
When t is 0, p is, so it's, what is it? P over 0 is equal to 1,000.
P of 0 is 1,000, right? So we know that when time is 0, the amount is 1,000, right? So this is the initial condition that describes the situation. All right, so now that we have that, that brings us to part B. Can we solve this differential equation? Sure, it's separable. And divide both sides by P. And then integrate both sides. 1 over P integral ln P. And integral of this
0.05x.
T
T.
is the variable we're using. And so now I solve for P, I raise both sides to the E, so I get P is equal to C e to the 0.05t.
Which is the PERT formula.
The PERT formula, right? This is where it comes from. Right? So we know that the C is normally the P0, right? But we can actually solve it here. Since P of 0 equals 1,000, it means that P is equal to 1,000 when T is 0, right? Which is just e to the 0, so that's just 1, and my C is 1,000. So then I can go back here and plug in that value for C. Right? So that PERT formula that you learned in 205 it comes from here. Right? Right? That's your P naught e to the RT. Okay. So that's the answer to part B. Let's go to part C. How long will it take to double your money?
So 200 is 2,000 equals to 1,000 to be 0.05t.
Sure. So how would I solve this equation? Obviously I need to solve for t, right? So
Divide by 1,000.
divide by 1,000, so I get 2.
Take e to both sides.
ln. So I get ln2 is just 0.05t. And so t is just going to be ln2 over 0.05. And notice that this is sort of a general thing. like the 2,000 and the 1,000 didn't matter. As long as over here was double there, when you divide, you'd always get 2. And then it would always be this, right? The time to double will always be ln2 over the growth rate, right? So that's that. Part D. How much money will you have after 6 years?
P. So P is equal to 1,000, E 0.056.
And 6. Right. So that's just 1,000 e to the 0.3. And you can plug that in your calculator and figure out what that is. But for now, P is that after 6 years. So that wasn't so bad. Of course, there are curveballs they could throw at you. They could think of a T in months, and then you have to watch the units and things like that. But overall, that's do it. Any questions?
In regards to calculators, are we going to be allowed to use them? On the
Yeah,
tests?
scientific calculators, yes. You can use them.
Would we have to give you the answer to that on the kind of exam, or did you calculate it out, or would you leave it in a formula and it's fine?
Like, for me, this is fine. Calculators really become important when we start probability and statistics, and you're going to really need them. But here, for me, it's okay to leave it with LNs and the answer and stuff, particularly the kids. Another example. Last example of the day. A woman gets 20,000. 200,000, right? 20,000, horrible. And she retires. And puts it into an account. Here's another example. The woman retires and she gets $200,000 when she retires. So she decides to put this in an account. Well, she gets 7% interest on her, but alright, she gets 7% interest per year, compounding continuously. But she's withdrawing some amount of money for her expenses. So she puts $200,000 in the bank. It's growing at 7%, but at the same time she's taking money out. $20,000 per year to be exact. Now I want you to write an ODE that describes the situation, solve it, and then answer these questions. Can we get the ODE here? Okay, that's the easy part. I know there's a DPDT in there somewhere. Okay, what? 0.07p minus 20,000. And of course, when I put 20,000, I'm assuming t in years, right? Because that's how much she's withdrawing per year. So it's growing by this rate, but she's diminishing its growth rate by that much per year. So how do I solve this differential equation?
Don't you need the initial condition?
Huh?
Don't you need the initial condition too?
Yes, I activate the initial condition. What's that?
If 0 is 20,000.
That's correct. Okay, so now that brings us to part B.
Have to take out 0.07 on both sides.
So it's highly recommended that you factor out the constant here before you move things to the other side. In 209, they make you do that because they expect you guys to forget the substitution when you move it over here. I have no faith. I have faith in you guys, though, but they don't. So this is what they recommend you do because a lot of students will forget to put that 1 over 0.07 when they do the integration over here. So they recommend that you factor out that constant and then divide both sides by this. And so you have dp over p minus 20,000 over 0.07. This you can integrate both sides, so you get ln 2000 over 0.07. So of course, raise both sides to the e, and then you get p minus this, and you add it to both sides, so you end up with p is equal to ce to the 0.07t plus 20 to the 0.07. Wait, is this a nice number, by the way? 20,000 divided by 0.07? Mine actually has a calculator. Maybe it's nice. I can just write that down instead.
Not a
Okay, so let's actually find that C. Since P of 0 is equal to 200, 1, 2, 3, that means I can plug in 200, 1, 2, 3 is equal to C e to the 0, because I would plug in t equals 0 here, plus 20, 1, 2, 3 over 1, 2, 7. And so I would get C is equal to what's that approximately? 2 decimal places.
200,000 minus. It's like a negative.
Okay, negative what?
Negative 85,714.29.
Okay, so my P would be minus 85714.29 e to the 0.07 t plus 0.07. It's negative, it's okay, it just means that it's decreasing. Her bank account is actually decreasing, right?
Makes sense.
So just that the interest rate isn't growing fast enough for her to for the bank account to go up. It's actually just diminishing slowly. So let's go to part C. How long can she actually keep this up? Obviously it's decreasing. When is her money going to run out? Right? How long can she be in retirement on this money?
So you have to set P equal to 0.
Right. Set P equals 0 and solve for T. Right? When is the balance 0? So all I do here is I plug in 0. Right? So how do I get to that T? Subtract this, then you're going to divide by that. So this is minus 20,000 over 0.07. You're going to divide that by minus 85714.29. And that will give you e to the 0.07 t. Where is that roughly? The exact number doesn't matter. Like if they expect you to use this, they'll tell you how many decimal places and so on and so forth. But for now, I just want to get through the example. So what's this number?
Yeah. 200,000.
This is 20,000, or divide that by 0.07. Then divide your answer by 857. 3.33. So of course here you ln both sides to get to that t. And so your t would be roughly ln of 3.33 divided by 0.07. Can you tell me what that is, roughly, as a number?
$17.2.
17.2. So in this situation, she puts her money in a bank account gaining 7% interest compounding continuously, and she withdraws 20,000 if she originally starts 200,000. She will actually run out of money in 17.2 years. Huh? What if she expected to die in 15 years? How much money does she need to take out to make sure she finishes her money and doesn't leave anything to anybody?
P is equal to, what is the equation? Negative 8, whatever that is, times E 10715.
It's trickier than you think, don't jump the gun. What are they asking you for here? They're asking for the H, right? If you want to run out in 15 years, what does your H have to be? It means you can no longer use H equals 20,000. You're going to have to go back to the original and just put H here and carry the H with you, right? Plug in P equals 0, T equals 15, and solve for the H, right? So it's a little bit more complicated. And the questions can get even more complicated. Sometimes they can say, what if she wants to withdraw 20,000 for 15 years? How much should she deposit in the original, right? Like, so then that 200,000 is what would have to change, right? So you have to be careful of what they're asking you for. So I think we'll stop there today. So your first quiz will be on Wednesday. It'll cover all this stuff that we've done. And we completed chapter 2, so the homework for chapter 1 and 2 are due Wednesday. So, remember in the syllabus, you just, look at all the chapter 1 homeworks and 2 and do them for Wednesday.